Section 3, quadratic functions and the complex numbers. Counting numbers would be 1, 2, 3, 4, so forth, 5, 6, 7. Integers, -1, -2, 0, 1, 2, 3. Those are integers. Rational numbers would be ratios of integers. Irrational numbers you cannot put into terms of a ratio. So pi would be irrational. Radical 3 would be irrational. Those are some examples of irrational numbers. And real numbers would basically be anything on the number line. So these are real. They're just, you can't put them as a fraction because they fall on the number line somewhere. So real numbers are numbers that are used for measurement that can be represented on a continuous number line belonging to the real number system. The real numbers consist of 0 and all positive and negative integers, rational numbers, and irrational numbers. One basic property of real numbers is that their squares are never negative. There is something that is not real. It's called imaginary, I. And I is equal to the square root of -1. If I square I, square root of -1 times square root of -1, you'll get -1. I cubed you could think of as I squared times I. So you could think of it as -1 times I, which is negative I. And I to the fourth, if you want, you could think of it as I squared times I squared, or -1 times -1, which is 1. Okay? If a is greater than or equal to 0, then the square root of -a, you could write as I square root of a. So let's simplify this. The negative will come out as an I. Square root of 25 is 5. So you just have 5i. Here the negative comes out as an I, and you just have the square root of 7. Example 3, -9, that would be 3i. The negative can come out. This would be 5i, but it's minus, so it would be minus 5i times 2 is -10i. Okay? 3i minus 10i gives you -7i. And you're done. Complex numbers. A complete number system, one that includes both real and imaginary numbers, was devised. Numbers in the set are called complex numbers. Complex numbers consist of all sums a plus bi, where a and b are real numbers and I is imaginary. A is called the real part, b is called the imaginary part of the complex number. If b is not equal to 0, then the number is called an imaginary number. Real numbers fit in the complex number system because if the imaginary part is 0, you have a real number. Pure imaginary numbers would be where a is equal to 0, and you only have the I part. Add. When you add, it's just like combining like terms. So 2 plus 4 is 6, 3i plus 5i is 8i, and you're done. Multiply is foiling. So you have 2 times 4 is 8, and then your outers and your inner. So you have 10 plus 12, 10i plus 12i is 22i, and here 3 times 5 is 15, I times I is I squared. And remember, I squared is equal to -1, so this becomes -15. -15 positive 8 gives you -7 plus the 22i. Example 6. Complex conjugates of a plus bi is a minus bi. Their sum is a real number. So if you add those two together, the imaginary parts will cancel out and you'll just have a real number. Their product is a non-negative real number. Okay? So I want to express this fraction in the form of a plus bi. If I multiply the denominator by its conjugate, I will get a real number on the bottom. So let's do that. I'm going to take the denominator and multiply it by its conjugate. What you do to the bottom, you have to do to the top. FOIL, so first outer inner last. When you do that, you have 20. You have negative 15 and negative 8 with the i's. Negative 2 and a negative 3 is positive 6i squared. 16. Outer and inner cancel out, minus 9i squared. Combine your like terms. Here you have 20. This would be minus 23i, and this ends up to be minus 6. Which I guess I'll get that in the next step. So I'm doing it in 2 steps. And there's that's your minus 6. Then minus 9i squared becomes a negative, minus a negative 9. Let's get there. So 20 minus 6. And here you have 16, it'll end up to be plus 9. 20 minus 6 is 14. So 14 minus 23i, 16 plus 9 is 25. And then you can just write it as 2 fractions if you want. So 14 over 25 minus 23 25ths times I. And you're done. Find real numbers x and y such that x minus 5i is equal to 2x plus yi. 4 is the real part. 2x doesn't have an I, so that's the real part too. So I can set 4 and 2x equal to each other. I can also set the imaginary parts equal to each other. The negative 5i is equal to yi, and then the y's cancel out, so you have negative 5 equals y. So you have y is negative 5, x is 2. And you're done. Find I to the 4th, I to the 8th, I to the 12th, I to the 16th. What can you say about I to the n if n is a positive multiple of 4? Well, I to the 4th is I squared times I squared, which is negative 1 times negative 1, which is 1. I to the 8th, I could think of it as I to the 4th times I to the 4th, which would be 1 times 1, which is 1. I can think of this, if I want, as I to the 8th times I to the 4th, 1 times 1. I to the 16th, hopefully you get the idea. It's 1. So any positive multiple of 4 will give you 1, no matter what. Okay? If I wanted to find, I don't know, I to the 71st, okay? What you could do is write this as I to some power that is a multiple of 4, as large as you can get, and then I to whatever is left. So 68 is a multiple of 4. So I could write that as I to the 68th times I to the 3rd. And so now I know this is 1, so I have I to the 3rd. So if you want, you can think of it as I squared times I, which is negative 1 times I, which is negative I. Okay? Another way, if you couldn't get that 68 and think of it, here's what you could do. You could do 71 divided by 4. So let's do long division there. 71 divided by 4 gives you 1, 3, 1, 2, 4, 6, 7, right? 28. Subtract, you get 3. So this gives you 17 with a remainder of 3. I to the 71st always equals I to whatever that remainder is. I'll just call it R, always. So that's a fast way to solve these.